Alright, in this video we're going to talk about chemical kinetics, which is the study of how reaction rates change in chemical reactions based on what's being done to them. So when we talk about a reaction rate, what we are talking about is how fast are either the reactants disappearing or the products appearing. You can look at it either way. When we measure the rates of reaction, those are going to be looking at how fast is the concentration of a species changing as time goes on. So it's not the amount of a substance per time, but it's the concentration, because as the concentration changes, that's really more what's going to be related to the rate rather than how much of something there is. When reactions happen, they always occur in multiple steps. So there's very few reactions out there that happen in just one step. So we'll talk about a little bit later, but for reactions to occur, molecules have to collide. And so if you have a reaction like this example here where it says two nitrogen monoxides react with fluorine, what's going to happen is that the odds of two NOs and one F2 coming together perfectly all at one time are just astronomically small. So reactions like this actually are going to occur in 2 steps, or many reactions are going to be even more steps. And so you can see we can break down this reaction of 2NO plus F2 to have a first step where an NO molecule and an F2 molecule collide together and they make an NOF2, what's called an intermediate. Okay, and then this NOF2 molecule can go on to collide with another NO molecule to make our final product. If we add the 2 steps together, we get the overall, but that overall is never actually happening. Okay, so again, this that underline, that NOF2 is called an intermediate. And that intermediate product is something that both gets formed and then used up by the reaction. So it's not there at the beginning, it's not there at the end, it's just there for some amount of time in the middle. Many reaction intermediates disappear almost as quickly as they appear because they're usually not very stable molecules, but some will kind of hang out for a longer period of time. Okay, so chemists can use knowing the steps to come up with an idea of what the rate law should be, like how the rate depends on the concentrations of the different species in the reaction. So what the rate law is, what actually governs how fast a reaction will go, will end up depending on which step is the slowest step. Okay? And the slowest step is known as the rate determining step. And we'll look at an example of why is it the slowest step that matters. So if the first step, the forming of the NOF2, if that's the slowest step, we'll get a very different reaction or rate law than if it's the second step that's the slowest. So if the first step is the slowest, then we're going to get a rate law that looks like this. Okay, and the rate will depend on the concentrations of the NO, and sorry, I guess I'm getting a little bit ahead of myself. These square brackets here means concentration of. So anytime you have something in square brackets, that equals the concentration of that in chemistry. Okay? So if the first step was the slowest, the rate would be this. Okay? And where it would depend on the concentration of NO and F2 equally. if the second step was slowest, you get a different rate law, okay? Because in the second step, there's still an NO in the second step, but then there's NOF2. And how much NOF2 is there depends on the first step. So if the second was the slowest, you would get your rate law would more likely look something like this. Where the rate is more dependent and has more to do with the concentration of NO because the NO participates in both steps. Okay, I'm just going to spend a little bit of time talking about why does it matter? Why does it matter so much what the slowest step is in terms of the rate? And so if we look at, for example, sending out a mailing. So if I want to send out a mailing, I have to stuff the envelope. And let's say stuffing an envelope takes me 5 seconds per piece of paper. I have to address it. And if I'm going to address it by hand, let's say that takes me 1 minute. All right? Then I have to put the stamp on it. And that takes 1 second. And then if I have to then seal it, let's say that also takes 1 second. Okay, so for sending out this mailing, if I was doing it by myself and I want to know, well, how long is it going to take to send out this mailing, I would add up all the times, the 5 seconds plus 1 minute plus 1 second plus 1 second. Okay, and so I get 1 minute, 7 seconds. And I would multiply that by the 100 or whatever mailings that I had to do. Now, however, in a reaction, okay, it does not matter how long all of the steps take, because when I'm doing this mailing by myself, I have to stuff the envelope and then I have to address it. Okay? But if let's say I had 4 people working on this mailing and one person was just stuffing the envelope and one person was just addressing and one person was just stamping it, one person was just sealing it, then what would happen is a bunch of envelopes will get stuffed in the time it takes to address it, and then once the addressing's done, the stamp and the seal would go on right away, and so only the addressing thing matters. So if I had 100 envelopes to do, it would take me 100 minutes to get this done. And of course, there's a little bit of time added on to that because once I'm done with the 100th envelope, it still needs to be stamped and sealed, and there was the 5 seconds before, but only the slowest step matters in terms of how long this takes. So again, this is when scientists determine a rate law, we can come up based on knowing a reaction mechanism, what the rate law should look like. A lot of times this has to be determined by experiment, and then once you determine the experiment, you can use what the rate law looks like to try to back out what the mechanism probably would be to lead to that rate. So the rate law always looks like this, where K is something that's dependent on temperature, because the rate of reaction is temperature dependent. So the higher the temperature, the higher K gets. And then you have your different substances. So there's just generic A and B, and they're raised to some sort of experimentally determined exponents. And we'll talk in a little bit here how you determine those exponents. Okay. And again, we're back to this, and so let's look at an example of how could we determine the actual values that go into a rate law based on experiment. So we have a reaction here, and we have some data. So we did 3 different experiments, and each time we took and we found what the concentration of our reactants was and how long the reaction, not how long, but what rate the reaction happened at. So we know that the rate law has to look something like this. The rate has to equal some number K times NH4 plus to some power A that we don't know, times NO2 minus to some power B that we don't know. All right? So how do we determine those numbers? Well, we look at a couple of different experiments. So if you look at, if I compare experiment 1 to experiment 3, if you notice, I can plug in the numbers for that. So I know the rate for experiment 1, the rate is 1.35. The K, I don't know K. The concentration of NH4 is 0.1 to some A power that I don't know. The concentration of NO2 minus is, I'm sorry, I don't want to compare experiment 1 to 3 because that has two different things changing. We're going to compare 1 to 2. Sorry. So the concentration of NO2 is 0.005, and that's raised to some B power. Now if I look at experiment 2, okay, the rate goes to 2.70. K is still the same number. NH4 stayed at 0.1. That's still the A power. And NO2 minus is 0.010. That's to some B power. If you look, I can divide these reactions out. If I do that, 1.35 divided by 2.70 is 0.5 equals, the K's cancel out, the 0.1 to the A power cancels out, and so what I'm left with is 0.005 to the B power over 0.010 to the B power. Since these are raised to the same power, I can just say that's the same thing as 0.005 over 0.010, all raised to the B power. So 0.005 divided by 0.010 is also 0.5. So basically 0.5 equals 0.5 raised up to the B power. So what power do I raise 0.5 to get 0.5? I raise it to 1. So now I know B equals 1. You should be able to determine what A is by comparing experiment 2 to experiment 3. So if you compare these two together, that will give you what A is by doing similar math, and we can take a look at this together. And then once you know what A and B are, you should be able to determine what K is for the temperature that this reaction was done at. Okay. I'm really not sure why I have this last. I probably should have talked about this first. Okay. But again, things need to collide to react. And they have to not just collide, not just bump into each other, but they have to collide with the right amount of energy and with the right orientation. So like two molecules can't smack together anyways. They have to hit in the right places and with the right amount of energy to make things stick together or fall apart or whatever needs to happen to make the reaction happen. Now, these reactions, they're not very likely, but molecules collide all the time at really high rates, and so that makes things that look really unlikely happen to us, it seems like, quite often. It's like your chances of winning the lottery are not good. But if you played the lottery 1,000,000 times every day, you'd probably win the lottery a lot. You just end up having to spend a lot of money. So the things that affect the rate, the nature of reactants. Some types of reactants will react faster than others. Like ionically bonded stuff are faster than covalently. If you have strong acids versus weak acids, the strong ones react faster. So generally, if things are less stable, they'll react faster. And if there are less bond rearrangements, you'll get a faster reaction. Okay. Temperature. The higher the temperature, the faster the particles move, so the more they collide, so the faster they react. Also, the more energy they have. Concentration. The more things you have packed into a small area, the more they're going to collide. Surface area. The more exposed surface area you have, the more colliding you have. And then catalysts basically give you an easier path for the reaction to take. Okay, so I think I only have 10 seconds left, so I really can't go into the boxer analogy, so I'll have to discuss that at a different time.